In our next lesson, we're going to look at implicit differentiation again, this time using it in the same way we've used all of our other derivative rules to find things like the equation of the tangent line or the equation of the normal line or horizontal tangent. We can use the implicit derivative the same way we have as any other derivative. So that's what this lesson is about. No new shortcuts or anything, just applying what we already know. So first, they want us to find dy dx. So we are going to take the derivative. So we have 3x squared plus 3y squared dy dx equals, and this is going to be a product rule, first times the derivative of the second, dy dx, plus the second, y, times the derivative of the first, 4, and then the 1 just becomes 0. So I want to solve for dy dx, so 3y squared dy dx minus 4x dy dx equals 4y and then minus 3x squared. Factor out the dy dx, and I have 3y squared minus 4x. And then I'm going to divide by the 3y squared minus 4x. So dy dx equals 4y minus 3x squared over 3y squared minus 4x. All right, then it says evaluate dy dx. It's talking about evaluating it at this point that they gave us up here. So they gave us our x and y. So we're just going to plug in those values for our derivative. So we're evaluating this thing at the point 2, 1. So we're going to have 4 times 1 minus 3 times 2 squared over 3 times 1 squared minus 4 times 2. So we get 4 minus 12 over 3 minus 8 is negative 8 over negative 5, or 8/5. So using our derivative, we get 8/5. Well, then it wants us to write the equation of the tangent line. Well, the equation of the tangent line requires us to know x and y and our slope, which we just found. So we're going to have y minus y equals our slope times x minus our x, or y minus 1 equals 8/5 x minus 2. All right, so our next example asks us for the equation of the tangent line as well. So we're going to start by taking our derivative. So we're going to have, that's 2y dy dx equals 4. So divide by 2y, and dy dx equals 2 over y. Now, to write the equation of the tangent line, we need x, we need y. So to get y, we're going to plug in here. We have y squared equals 4 times 1. So y squared equals 4. So I take the square root. So y is going to equal plus or minus 2. So that means that we're going to have actually 2 tangent line equations and 2 normal line equations, because we could have x is 1 and y is positive 2, or x is 1 and y is negative 2. So when we're evaluating our derivative for our slope, remember you're going to need to evaluate 1, 2, and then you're also going to need to evaluate the derivative at 1, negative 2. So for the 1, 2, the 1 in our derivative is irrelevant, so we just get 2 over 1 is 2. 2 over 2, that's a y, is 1. The x is irrelevant. And when I plug in for 1, negative 2, I get 2 over negative 2 is negative 1. So when I'm writing my tangent lines, I'm going to have 1 for the point 1, 2. So the tangent line for 1, 2, we have y minus 2 equals our slope 1 times x minus 1. And for the point 1, negative 2, I have y plus 2 equals negative 1 times x minus 1. All right, then for my normal lines, I'm just going to change the slope. Well, 1 over 1 flipped is still 1. So we change the sign, we just get negative 1. So this one's just going to be y minus 2 equals negative 1 times x minus 1. And this one is going to be y plus 2 equals, flip it and change the sign, we get positive 1 times x minus 1. All right, so next they ask us about where the tangent line is horizontal and where the tangent line is vertical. Well, we're used to this question. Where is the tangent line horizontal? Well, that's where the derivative is 0. The horizontal tangent line is when the derivative equals 0. So we're just going to take our derivative. In this case, it was 2 over y, and set it equal to 0. And so 2 over y equals 0, multiply both sides by y, we get 2 equals 0. Well, that's not possible. So that means there is no horizontal tangent line on this graph. Now for the vertical. Well, we know a vertical tangent line is going to occur where there is no slope, or where the slope is undefined. A vertical line is where the slope is undefined. So here we could use 1 over 0. So anytime they're asking you for a vertical tangent line, we're going to set our derivative equal to 1 over 0. So I have 2 over y equals 1 over 0. So I could cross multiply here and I get 0 equals y, or y equals 0. So if it asks me for where this occurs, I might want to put that 0 back into my original equation. The original was y squared equals 4x. So I'd have 0 squared equals 4x. So 0 equals 4x divided by 4. X is also 0. So there is a vertical tangent on this original graph, at x equals 0, or at the point 0, 0. Now, you don't have to know what this graph looks like, but I want to go back and just show you so that this vertical tangent thing maybe will make more sense to you about where it is and how it occurs. So back up here, if I were to solve this equation for y, I would get y equals plus or minus the square root of 4x, or plus or minus 2 square root of x. Well, the square root of x graph, remember the positive square root graph does this. Sorry, I don't know if you can see what I was doing. The positive square root graph does this, and the negative square root graph just flips it over this way. So it's a sideways parabola here. And so at our point 0, 0, these slopes were coming down until they got to the point where they were straight up and down right there. At the point 0, 0, we had a vertical tangent line. So that's what we were talking about. There's no horizontal tangent line because this slope, this graph just keeps growing. So there's not ever going to be a place where we have a horizontal tangent. So I thought maybe that would help you with understanding these two answers right here. All right, next we're going to find the second derivative of y with respect to x. So let me explain just a little bit about the notation for why it looks like this. So for our first derivative, we've talked about the fact that we were taking the derivative with respect to x of y, and we get dy dx. So for the second derivative, we're taking the derivative with respect to x of dy dx. So we end up with d squared y over dx squared. So that's where this weird looking notation comes from. Oh, sorry, once again, I keep doing that. All right, but that's all they're asking. And we already found our first derivative. Our first derivative, we did that up at the top, was dy dx equals 2 over y. So now we want to take the second derivative. So we're going to use the quotient rule. We have the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Or negative 2 over y squared. Ooh, bottom derivative of the top minus the top derivative of the bottom, I forgot my tag, dy dx. So we have negative 2 dy dx over y squared. All right, so we're going to need to plug in our dy dx. So we get negative 2 times 2 over y, because remember dy dx, we already defined it over here, over y squared. Or negative 4 over y divided by y squared. Remember, we can keep change flip. So we get negative 4 over y cubed. So whenever it asks for that second derivative, where our first derivative falls in that problem, remember we can just substitute what we had here for our first derivative.